In this video, I'm going to talk about product manifolds. So if we first consider a few simple examples, so let's take the product of the circle S1 with the real line R. So the product S1 cross R is a sort of infinite cylinder. So if you imagine a cylinder that sort of extends forever in both directions, then this is the product of S1 and R. A different example of a product, if we take the product of two circles, then this forms a torus. So, and we can see that we've got one circle, maybe if this circle is the blue one, and if this circle is red, we can see this circle going around the hole like this. And then any point on the torus we can see is where one copy of this red circle meets one copy of this blue circle. So this is sometimes called T2. This is the 2 torus, and this is the product of S1 and S1. The N torus is the product of N copies of S1. And it's a bit harder to visualize in high dimensions, but you might recall that we can build a 2 torus if we start with the unit square and identify the opposite sides. So if we glue together the two red sides and we glue together the two blue sides, we can build a 2 torus. Gluing together the two red sides builds a cylinder like this, and then the two red sides become a sort of single line because they're glued together. And then if we bend this round to glue the two blue sides together, this builds the torus like this. So these are some examples of product manifolds. So given manifolds M1 up to MK, of dimensions N1 up to NK, the product space M1 cross M2 all the way up to MK is a manifold of dimension N1 plus N2 all the way up to NK. And so why is it a manifold? Well, firstly, why is it Hausdorff? It's Hausdorff because the product of Hausdorff spaces is Hausdorff. It's also second countable because the product of second countable spaces is second countable. So the only thing we really need to check is whether the locally Euclidean property holds. So given a point with coordinates P1 up to Pk in this product space, we want to check, is it true that this is contained in a chart? So, well, for each I, Pi in Mi is contained in a coordinate chart, Ui phi I, because Mi is a manifold. And so if we consider the product map, phi1 cross phi2 up to phi k, which goes from u1 cross u2 up to uk, and its image is in R n1 all the way up to nk, this is a homeomorphism onto its image. And the reason it's a homeomorphism is because each of the phi I are homeomorphisms onto their images. And therefore, we do have that each point P1 up to Pk is in the image of a chart, is in the domain of a chart. So this point is in the chart, u1 up to uk, phi1 up to phi k, and therefore it is locally Euclidean. So therefore we can say that m1 up to mk is a topological manifold of dimension n1 plus n2 all the way up to nk. Okay, so as we said at the beginning, there are various examples such as the n torus, which is S1 cross S1 n times. This is an n manifold. And I'll just end with a little bit about the 3 torus. So a nice way to visualize the 3 torus is to think about if we start with a unit cube. So this unit cube is 0, 1, cross 0, 1, cross 0, 1. And just like we did for the 2 torus, where we glued together opposite sides, opposite edges, we're now going to glue together opposite faces of the cube. So the red face at the top, we're going to glue to the red face at the bottom. The blue face on the right, we're going to glue to the blue face on the left. And the 2 faces I haven't shaded at the front and the back, we're also going to glue those together. So it's hard now to imagine what you get once you've glued all of those together, but you can imagine what it's like to live inside such a world. If you live inside a 3 torus, then it's like walking through this wall on the right, you'll come out through this wall on the left. And if you go up through the ceiling, you'll come out through the floor, and so on. So that's just a little bit about what it would be like to live inside a 3 torus.